the University of Nottingham, and my colleague John McMaster, who's here, who is the admissions tutor, who knows all about how to apply to university, and he's doing a workshop later, so I'll let him talk about that. So the aim of my talk is to try and show you how you might judge how good an idea is for a sixth form science project. And I've written here my, because my in some ways means you personally, but it's also because I'm going to use my experiences at school to try and illustrate what I think is good and bad, and because I can criticize myself without offending anybody. So let's begin a bit about myself. My title is Research Professor in Chemistry at University of Nottingham, and I work in an area called green chemistry, which I will tell you a little bit later. I was born in London, and my father was Russian. I've already met one Russian pupil here. How many Russian students are there here? Привет. And both my father and my Russian grandfather were physicists. So the question was, what would happen to me? And really, I didn't have any choice at all. My father decided that I should be a scientist. I'm not sure exactly where this photograph was taken. I think it was taken in a place called St. Margaret's Bay, which is on the coast quite close to here. And this is about the total extent of my life as a biologist. And my earliest memory is actually sitting in my pram, and I remember now, and I think it's true, that I noticed that if I put my hand to my ear, like this, I could hear the wind, and that it sounded funny. But I don't really count that as being science, because I didn't try and produce an explanation for this. And my earliest scientific experience I can remember was when I was in bed. I think it was probably a year or so after this photo was taken. And when I was lying in bed, I noticed, this is not me, but I noticed that this ear, the one sticking up, got cold, and the one on the pillow was hot. And so I thought this was quite strange, so I came up with an explanation. And my explanation was that there was a metal rod inside my head, which was taking the warmth from this ear and conducting it downwards. Now, if you think about this, this is a scientific hypothesis, but you can criticize it. First of all, it contradicts the second law of thermodynamics, which obviously I didn't know in those days, which says that heat cannot flow from cold to hot. The second thing was that there is nothing metallic inside one's body, unless you've got a hip implant or something like that. And obviously, aged 5, I didn't. But the worst thing was that I couldn't verify it experimentally, so it was not a good theory. But, and this is quite interesting, it did suggest the correct way to make my cold ear warmer, which was to turn over in bed. So it demonstrates that even if you have a completely crackpot scientific theory, it can actually help you do the right thing. So then, aged 8, I went to boarding school. Here is the school photo, and I'm there. And I'm sorry to say that I hated it to begin with, because I hated the food and I wasn't good at sport. And this is a letter I wrote on the 5th of March 1957. Dear Mummy, this note is only to tell you I'm rather miserable. Please send me something to cheer me up, a toy if possible. Love, Martyn. SOS Distress. This letter was a disaster. My parents telephoned the headmaster. I was summoned to the headmaster's study and asked what was wrong, and I didn't get a toy. And I went on hating the food. But one of the problems that I had was that I couldn't swim and people made fun of me. So I came up with what I feel was my first scientific hypothesis. I decided if I jumped into the deep end of the swimming pool, I would have to swim. So this was a good hypothesis because you can test it experimentally. So I jumped into the deep end. You imagine an empty swimming pool with the whole school, not as many pupils as here, I think there were 90 odd, standing around watching the mad Poliakoff jump into the pool. And the result, as you must expect, was that I sank to the bottom and I had to be rescued. Now, what this actually demonstrated to me is something that often happens in science, that it's a good experiment, but it answers a different question from the one you thought of. And in my case, it answered the question, how do you become a hero in the school? You know, the headmaster said, look at Poliakoff, jumps into the swimming pool. So if the Young Scientist Journal had existed, I could have then submitted a paper called How to Become a Hero in Your School. But as you know, that scientific papers have to be refereed, read by other scientists and judged. And so what I think the referees would have said was that it wasn't a good paper because the experiment was only done once, so I didn't demonstrate whether it was repeatable. And you can also see that the method won't work for everybody, because if you could swim, nobody's going to be impressed if you jump into the swimming pool. And the other thing is, even for me, the method was unreliable. If the school had caught fire the night after I jumped in, the people who had rescued the pupils from the burning building would have been the hero, and they would have forgotten me. So it would have been rejected as a scientific paper. So, but I got at this stage quite excited about the possibility of science, and there were no books at all in the school science library about science. So I had to find my own books, and I began with my mother's science book, which was published in 1902. That was 11 years before my mother was born. This book was quite fun. It was like a play with Big Brother talking to two younger siblings, telling them about science. I learned almost nothing from it. I then was given this book by Andrade and Huxley, was a Nobel Prize winner, called Science Forces at Work, and you can see it says, for Martyn Poliakoff with every good wish. And again, this book had quite a lot about chemistry, but I didn't really learn very much about it. But the book that did have a big effect on me was one with a rather unlikely title, Romping Through Mathematics, by Raymond Anderson. And there was one page, the important page here, which was about Galileo, and it describes how Galileo, who's here, was sitting bored in a church service in the cathedral in Pisa, and being at the boarding school and going to many church services, I immediately empathized with the bored Galileo, and it described how Galileo watched one of the chandeliers, there isn't a chandelier here, which was swinging, and he timed the pendulum, and he did it by feeling his pulse. So I was rather more technologically minded. One of my friends had a stopwatch, and in one of the prep periods when we were meant to be doing our homework, I got out the stopwatch and I had a piece of chain, and I hung all the pieces from my geometry set, compasses, set squares and so on, and made a pendulum and started timing it. And I got really engrossed, and then the master came up and said, what was I doing? Why wasn't I doing my homework? I was to stop it at once. And this has an important lesson, which is that if you want to make science exciting at school, you should tell the pupils they are forbidden from doing it. And immediately it becomes something really naughty, you must do it. So I was hooked. though I'm not sure that was what the teachers had in mind. Now, if I just jump forward a minute, when I was about 16, my parents took me to Pisa. This is the cathedral in Pisa. This is the Leaning Tower. And we went into the cathedral, and there was a chandelier, and there was an American talking very loudly, saying he had written a book about Galileo, and would the attendants make the chandelier swing? And my father, much to my acute embarrassment, rushed up to this chap and said, "My son has read your book." So there I was, as you can imagine, totally tongue-tied, unable to say anything. So the message to you is, when you're grown up and have children, don't embarrass them. So, now we go back to my schooling. I went to a school, started science at the age of 14, and here. My school was quite old, but 960 years younger than this school. And I started science. This is my first inorganic chemistry book. And what was interesting about this book is that it did not have a periodic table in it. This book was written in 1961, that's 99 years or 98 years after Mendeleev proposed the periodic table, and it didn't have one in it. So I bought my own, and this is my first periodic table. If you are keen on chemistry and sharp-eyed, you will see the element argon is, in those days, was shown with the letter A rather than AR. I'm not sure where argon is on my tie. AR, which is the modern symbol. And so I enjoyed chemistry. I was a dreadful pupil. I talked all the time in chemistry lessons, but I could answer all questions, so the teacher didn't know what to do. And I set up a lab in the basement of my parents' house. It had an extra story, but that's been cut off by the caption. So this was my bedroom, and this was the lab in the basement. And there was a kitchen next door where I could also heat things up. And so I made an awful lot of mistakes. The one I remember most was that I tried to distill formic acid, this is formic acid, out of oven cleaner, which is a mixture of formic acid and water, and I didn't realize that the boiling points of the two liquids, water and formic acid, are only 2 degrees centigrade apart, which means it's almost impossible on the small scale to separate them by distillation. Anyway, I made a real mess of it, and I superheated the solution, put in some boiling chips, the whole lot went whoosh, and the entire basement was filled with fumes of formic acid, and the basement had to be evacuated for some time. But so you must be careful doing experiments at home. But then, for reasons which I can explain to you afterwards if you're interested, that by the age of 16 and a half, I had taken all possible exams in chemistry in this school, A-level, etc. And I was a whole year ahead of everybody else in my class. So the school didn't know what to do, so they just told me to do experiments while the rest of the people were doing their regular classes. So I did a research project, and I have absolutely no idea how I thought of it. And now you'll see it was... So this is I was very pompous in those days. So this is the front page of my notebook, the reaction between copper chromate and ammonia with occasional references to copper sulfate. And so, although I never actually wrote it down, what I was trying to do was that copper ions react with ammonia and in the present chromate to make a complex of copper and ammonia where there's a number of ammonia atoms, and what I was trying to do was to find this value of X. And So there I was, and I started doing masses and masses of experiments, because every chemistry lesson, there I was in the lab, beavering away without listening to what the teacher was saying. So I did precipitation and weighing, and there are pages and pages of this in my notebook. And then I did titrations measuring the pH, the acidity of the solutions, and this went on for a bit until I broke the pH meter. The pH meter cost £5, which was a really huge sum. It was 1% of the school fees for a year, so it was quite... I was absolutely terrified of what the school would say. Fortunately, they didn't charge me for it. I then did a lot of chromatography, with paper chromatography. You can see here, you put the iron, the solution there, and then you have a liquid, usually water, going up, and the ions travel up the paper. And again, I did hundreds of these, so each of these is one experiment, and I chopped the paper in half so that I could make the ions visible, because most of them are colourless, either by spraying with lead nitrate for the chromate or with hydrogen sulfide. And so again, there are pages of this, and I decided that it'd be really nice, instead of having to do this, to actually measure how these colourless ions were going up the paper. So I built equipment to measure the electrical conductivity, because ions are positively and negatively charged. They conduct electricity of the paper. So this is the first version of the equipment. This is the second one, which was a bit more complicated. And here is the result. This is one of the strips of paper, and I had a cell here, and as the solution went up, you can see I measured the conductivity. I'm absolutely amazed now. How could I possibly have had such patience to do such a thing? I wouldn't ask one of my students to do this, let alone try and do it myself. And you can see this took a whole hour or 56 minutes to do. And then I got quite carried away, and I tried to do what's called electrophoresis, which is where you put a high voltage on a piece of paper and you hope the positive ions go one way and the negative ions go the other. And so you can see here's the thing, positive end, negative end. And what amazes me, I just think that teachers probably weren't even watching what I was doing. They allowed me to use 450 volts, that's double mains voltage, on a piece of paper in the lab. And fortunately, I survived, though it might explain my hair. So then, because these solutions are coloured, I realised that copper chromate and ammonia, the mixture was green, and I realised that copper sulfate and ammonia is blue, and chromate is yellow, and blue plus yellow makes green. So I decided to do spectroscopy, looking at the absorption of light. And the school in the 1960s was not very well equipped, and they had a thing like this, which was called the spectroscope, and you put a sodium lamp at this end and you look through the telescope. And this is the spectrum of a sodium lamp. So I put my solution between the lamp and the spectroscope, and I counted which lines were there or were not there. And this is my notebook. Cross means it wasn't there, red spot means that it was. This piece of page is quite interesting because it was the height of modern technology, because this was written with one of the very first felt tip pens that you could buy in the UK. People got really excited, you see, that you could go to a shop and buy these felt tip pens. And this was written with one of the first felt tip pens, in fact two, a black and a red one. So I was really proud of this. But the upshot of all this was that all I learned was the reaction was a lot more complicated than I thought. But even I thought it was a bit stupid having to sit there measuring each line. So I decided to build a spectrometer. So with my friend John, we built a rapid scanning spectrometer. And if you look inside, it had a disc that span round and round. I've forgotten where the motor came from. And the disc had a series of filters, so red light, green light, and so on would go through and spin round and round and display the whole thing on an oscilloscope. If you don't know what an oscilloscope is, you can Google it afterwards. I can't remember very much except that this tube here came from the handle of my parents' vacuum cleaner. The vacuum cleaner broke down, and before my parents could get it repaired, I had dismantled it and sawn out a piece of the metal tube to make a test tube holder. So this, in principle, was a really good concept. It never worked, for reasons, again, that I can explain. So the real thing that was wrong with my project was that none of the teachers knew enough chemistry to tell me that the value of X here is not constant. It changes depending how you dilute the solution, how you change the acidity, and so on. So it could never have worked, but I was never told that. So I then went to university, and I studied chemistry, and I very nearly failed my final exams. You do not have to have brilliant university exam results to become a professor, so that is a good take-home message for you. I then studied for a doctorate, and because of my background, I became a spectroscopist, and I did photochemistry, which is studying the chemical effects of light. And so this is my doctoral thesis. You can see here are spectra. It was published, finished in 1972. And then I moved to the University of Newcastle, and here I am with hair of considerable size, and when I was in Newcastle, we designed and built equipment for spectroscopy and photochemistry. This is actually one of my students, Brian Davis. You can see his hair is rather miserable compared to mine. And this equipment, or a version of this, is still in operation at University of Nottingham, where I work now. And here I moved to Nottingham. I had a very small office when I started. I had to have two blackboards, one for me and one for the students. And you can see it wasn't tidy, and as John will say, that my office is still not tidy, 30 odd years on. And when I was in Nottingham, I became fascinated by so-called supercritical fluids. Supercritical fluids are gases like carbon dioxide or steam that are compressed till they're nearly as dense as a liquid, and they can be used as solvents for chemical reactions. So we then, about this time, the early 1990s, I became also interested in green chemistry, which is the study or devising of ways for cleaner ways for making chemicals and materials with less pollution. And this particularly highlighted the need to have cleaner or greener solvents for doing chemical reactions. And because I was working in supercritical fluids, I started using these. And as one example, we did continuous reactions of hydrogenation. Hydrogenation is adding H2 to organic compounds, to carbon compounds. And so you take the thing you want to react, the substrate, and hydrogen and carbon dioxide, mix them up, pass them through a tube that contains a catalyst. The reactor turns to product, and here you release the pressure, the supercritical fluid turns back to an ordinary gas, and the product comes out. And here's my colleague Pete Licence with the equipment. There's the stirrer there, the reactor there, and the product comes out at the bottom. And I used to say that it was as easy as milking a cow to get the chemical out. And then I gave a lecture in Moscow, and there was huge whispering in the audience, and I got quite worried. And I asked them what the matter was, and they said, we're discussing whether you've ever milked a cow. And I haven't milked a cow. Has anyone here milked a cow? And it turns out, I think, that this is easier than milking a cow. So, and then we were fortunate enough to work with a company in Durham, in the northeast of England, and we built a 1,000 tons a year chemical plant for doing these chemical reactions more greenly. And you may think that professors of chemistry every day go out and build chemical factories, but it's quite unusual. It was really exciting for me. In fact, made me interested in doing chemical engineering as well. So nowadays, that was a few years ago, we still measure spectra, and we still do photochemistry. And this here is involved in cleaner ways of making antimalarial drugs, particularly the drug artemisinin, which last week was the subject of the 2015 Nobel Prize for Medicine. And not for me. Now, the first question is, why have I become successful as a chemist or a scientist? And the real reason that I've been successful is because I've always had outstanding people to advise me. And so this is Jim Turner, my PhD supervisor, who supervised my doctorate, in fact still lives in Nottingham, came to listen to me giving a lecture yesterday. And here, and I'm sorry, this is not a very good photo, you can see there are 5 scientists, and the middle is Jim's PhD supervisor, Norman Shepherd, then there's Jim, then there's me, then there is Mike George, who's one of my PhD students, and then this is Dr. Sun, who is one of Mike's PhD students. And like a family tree, you can go back. So there's me, and then Jim Turner, Norman Shepherd, and then you can go right back to the 18th century. So my scientific great, whatever, grandfather's Berzelius, who's a Swedish chemist, who is very famous for, he discovered 4 elements. He invented the term organic chemistry. He also invented the word catalyst. And it's actually easier than doing a family tree because you only have one parent. If you're a scientist, if you're in your genetic family tree, you have 2, so it gets bigger and bigger. So, and this is my current research group, and I'm really grateful to them because they're the people who helped me go on to do science now. So, we now come to the aim of my lecture, which is to help or suggest to you how you might decide whether a particular project is good. And so, you must understand, I don't teach sixth form students, but just thinking about my project, I came up with a list of 12 principles, which if you are good at crosswords, you will see the first letter spells Yang Science. And so if you take these questions, let me just apply them to my project. So the first question, is it interesting? And I'm not sure whether my project was interesting. And has it been done before? I have no idea whether anybody ever studied the reaction of ammonia and copper chromate in such detail as I did. Would it be understandable to everybody? And the answer is clearly no. I don't think my parents ever understood what I was trying to do. And was it too complicated? And the answer is it was far too complicated for somebody to do at school I mean, it was fun, but it wasn't. And was there good advice available? I had very nice teachers, but they didn't understand how to do scientific research, so they could just look at amazement at this crazy schoolboy. Was it scientifically sound? And I think the answer is yes. I did sensible experiments. The other thing is there wasn't a clear question that I was trying to answer. I just went off at random and did all sorts of experiments. It would be fun to try electrophoresis or whatever. Could I do individual and group work? Well, I did stuff by myself. I worked with my friend John. Whether two people makes a group, you can ask or not. And was there an existing theoretical background? The answer was definitely yes, but nobody had told me about it. So, and it wasn't too expensive, so it was okay. And it was fun. But the chances of success was pretty minimal. So if you add it up, I should have probably done a different project. So I just think this might be quite a useful way, if you're thinking of doing projects or devising them, that you could use this.